Linear charge distribution is the case where the charges are being distributed over one particular line in a uniform way. Okay, the charges are being distributed over one particular line in a uniform way. So when this happens, what we do is, after we want to calculate the force that is going to be applied by this particular linear charge distribution system. So out here, this is a line where the charges are being distributed linearly, and what I do, I bring one particular test charge. Okay, this Q naught is a test charge. The concept of a test charge means it's like we want to verify how much is the force in that particular area, okay, by some other charges. Okay, it's like we are trying to take a test. For example, even for your cases, like when we take a test, it means we want to verify how much you have learned. Okay, same is in this particular case, a test charge. So Q naught is one charge which is going to experience an electrostatic force by this linear charge distribution system, where the charges are being distributed uniformly over the entire line. Now in this case, if I place this Q naught out here, it is going to mean the same because it is continuous. That is, charge is being distributed uniformly. So if I place this Q naught here or any side of the board, okay, along with this, it is going to experience the same force at any point. So for my convenience, I am keeping it on this point, and this R is the position vector of this Q naught. What I do, instead of doing it for the entire line, I'll take a small element from this line, this small element dl from this particular line, okay, and then I'll verify how much is the force being acted upon Q naught by this small element dl. Okay, and then what we do, take the integral of this dl for the entire line to see how much is going to be the electrostatic force acting upon Q naught by this entire line. Okay, it is going to be the same because it is being uniformly distributed. So what you do is, for convenience, take a small part first, okay, then take out the expression for this small part, and then you integrate for the entire line, and then find out the particular equation. So in this particular case, when the charge is uniformly distributed over the length of a conductor, it is known as linear charge distribution, also known as linear charge density, and it is denoted by this particular symbol called lambda. Okay, and its unit is coulomb per meter. Per meter because it is like 1D. The scenario is like 1D. Okay, where it becomes only meter. When you take it for 2D, it becomes meter square. When you take it for 3D, that is volume, it becomes meter cube. So this is charge per meter. Out here, I can write this lambda, that is linear charge density, as dq by dl. Okay, dq is the small element of charge which is here, okay, acting upon Q naught, and dl is the small element of the length taken from this entire part. So now what we do is, we take the force df. Now df is the small element of force acting upon this Q naught. Okay, so it becomes df 1 by 4 pi epsilon naught Q naught divided by r square. Out here, I should have written it in this form, dq. Okay, this particular expression that you get out here is the same expression just like in Coulomb's law. Okay, where you wrote F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by r square. This is what we wrote, okay, in case of Coulomb's law. Now in this case, what we are considering, Q1, the test charge, Q naught, this is what you can consider as one charge, and then Q2. Out here, what is acting like Q2? This small element dq, small element of the charge dq is acting like q2. Hence I can write this equation in this form: df, small element of the force, 1 by 4 pi epsilon naught q naught dq by r square, and the unit vector r. Okay, now in this case what I do is I substitute for dq. Okay, I have dq out here. I'll substitute for dq. Since dq is equal to lambda dl, therefore I can substitute for dq as lambda dl. Okay, I got the equation. Now what I do, since the charges are being uniformly distributed, just do the integration of the entire charge. Force, the total force will be equal to the line integral of 1 by 4 pi epsilon naught q naught lambda dl divided by r square with a unit vector r. So the last equation becomes f is equal to q naught divided by 4 pi epsilon naught integral lambda dl r square and unit vector r. So this is your force acting upon that q naught by this linear charge. Okay, the charge that is getting distributed linearly over this particular line. Okay, so this is the expression that you get.